Hello, I'm Mrs. Schroeder, and today we are going to talk about atomic theory. In your book, this covers section 1 and the beginning of section 2 in chapter 3. Couple of things in chapter 1. Early scientists didn't know what an atom was. They were trying to experiment and understand about the world around them, and they came up with this law of definite proportions based on weight of materials. They found that chemical compounds always contain the same amount of elements in exactly the same proportions by weight or mass. And it doesn't matter where it came from. Salt, like if we look at the crystal structure, or if it's coming from a salt shaker or from a dump truck, will always have the elements chlorine and sodium in these ratios, 60% chlorine and 39% sodium. Now by atoms it's a 1-to-1 ratio, but early scientists didn't know what atoms were. So all they could do is look at the weight of something. They also came up with this law called the conservation of mass. No matter what they did in a chemical reaction or physical change, they found that mass is not created or destroyed. It remains the same before and after. An example of that, if you take hydrogen and oxygen and you react it to form water, if I add up the amount of hydrogen by mass and the amount of water by mass, I would find that this mass before is equal to this mass after. It always stays the same. And we're going to try a little demonstration in class. We'll do for tomorrow. The law of multiple proportions is also something that chemists were trying to rely on. And this law is a little more complicated because sometimes different elements can combine to form different compounds. Now, scientists didn't know what the compounds looked like, but they did know that there was nitrogen monoxide and nitrogen dioxide, and they could react to form two different kinds of materials, a colorless gas or a poisonous gas, kind of a brownish color. But they didn't know this stuff. This was stuff they didn't know yet. But they could measure the mass. They could react it, break it down into its elements, and measure the mass. And they found that they always had 16 to 14, or this ratio of 1.4 grams of oxygen to 1 gram of nitrogen. And for nitrogen dioxide, they always had this ratio, 2.28. And what they found, law of multiple proportions, means that between this and this, there's always a proportion, a whole number, times 2. Or it might be times 3, depending what the proportion is for that compound. And we'll go over this in class also. Let's talk about law of multiple proportions in more detail. Now, today we know certain parts of the atom. We know there's an electron, a subatomic particle that has a negative electric charge. We know a neutron has no charge and is found in the nucleus. Okay? And we know a proton is something that has a positive charge, written like this, positive. It's also found in the nucleus. Okay? So we know that now. But the question is, how were these discovered? How do we know that? Atoms are very, very tiny. We can't see them. Well, a long time ago, Democritus started suggesting that the first thing about atoms, he said, matter is indivisible piece of matter made of, he called them atomos. He thought they were just different shapes for different elements. And he was ridiculed in his time. Nobody believed him. It took a long time before this idea began to catch on. Dalton is the first person really credited with this whole atomic theory and bringing things forward. He figured out that elements were made of one kind of atom, and atoms could combine. This is where the law of multiple proportions and law of definite proportions comes into play. They could combine to form compounds. And we're going to use these little ball and stick models in class that look kind of like Dalton's models. This is his model. Little wooden shapes that have little holes. You can poke them together and make different atoms. And that's what he thought atoms looked like. He came up with this theory. Make sure you write this down. Number one, he said all matter is composed of extremely tiny particles called atoms that cannot be subdivided, created, or destroyed. He also said atoms of a given element are identical, and different elements are different. He also said that elements combine in simple whole number ratios to form compounds. And number 5 is the law of conservation of mass. Atoms are combined, separated, or just rearranged, but never created or destroyed. And that was Dalton's atomic theory, these 5 points. Now, since Dalton's time, we have found that the first 2 principles are not always true. We'll find out that this one and this one sometimes there's sometimes changes. There's sometimes atoms can actually be broken down into smaller pieces, but they're not the same element anymore. And atoms are not completely identical, something called isotopes that we'll talk about later next week. Now, J.J. Thomson came along, and he used something called a cathode ray tube, and he discovered electrons. And I'll show you this more in class. I have a demonstration to show you, some videos to show you, but he came up with this idea that electrons are floating around in this cloud of slimy, murky stuff, but it has a positive charge. So he understood there's positive charge and negative charges. And this cathode ray tube, he was actually able to create a beam of electrons within the tube and understand that using magnet he can make them reflect back and forth. And he could change that tube because they had a charge. So he understood there was a charge. He understood that things could move. But his idea was that all of this is just one big circle. But instead of being like Dalton's just hard wooden sphere, it was actually this fluid where charges could move about. A couple of videos we'll watch in class tomorrow. Ernest Rutherford came along and perfected or worked on that model a little more. And in 1909 he performed the gold foil experiment. It's one of the most famous experiments in the atom theory. He discovered that the atom was mostly empty space with a nucleus in the center. Nucleus being the central region that has protons and neutrons in it. He didn't understand this part yet, but he knew there was a central region with protons. He didn't understand about neutrons yet. His atom model looked more like this. Instead of being the plum pudding model, it had a central nucleus and then electrons scattered around it. Now, how did he come up with this thing? Well, he took his gold foil experiment, took a very thin sheet of foil right there, and he placed it in the center of a fluorescent screen. That's a screen that will measure when a radioactive source hits it. And he took over here and he shot beams of alpha particles at this foil. Now, if I were shooting a bullet, shooting a gun at a sheet, I would expect it to go right through the sheet. Sheets aren't very thin, aren't very strong. It should go right through the sheet. So imagine his surprise. That's what he expected. He was very surprised when he found that when he shot these alpha particles at this very thin sheet of gold, some of those particles bounced back. Some went straight across like he expected. Some were deflected a little bit, but some bounced back. That's how he knew there was something dense in the center of the atom. And that's where he came up with the idea of a nucleus. Some problems with his model, though, is he couldn't explain why the electrons don't crash. If positive and negative charges, opposites attract, how come the electrons don't just crash and stay stuck into the center of the nucleus? And he didn't understand that. He couldn't explain it with his model, because what his model said is if I have these negative electrons out here, as they're moving around they should eventually hit here and stick, so that it would look like this with these little negative electrons stuck all over the nucleus. But it doesn't look like that. It doesn't do that. So why? This is where Niels Bohr came along, and he proposed electrons travel in specific energy levels. So there's a certain distance from the nucleus. And this is what we believe now, that there are certain regions of probability, or regions where the electrons exist. Just like a person climbing a ladder, if I'm climbing a ladder, I'm not very stable if my foot is right there. I'm in between rungs. I either have to go up or I have to go down to one of those rungs. I'm not stable in the middle. Electrons are the same way. They're not stable in different levels. They either have to go up to a higher level or down. And he's got levels. You can see the rings in here, the lower rings, and he's got higher rings that are farther out. He's trying to show it in 3 dimensions and on a 2D plane. But if I had an electron that was right here, it would not be very stable. It would either have to go out to this one or down to there. And that's what Bohr proposed with his model. So tomorrow in class we'll watch a couple of these videos and a couple little demonstrations, and then we're going to try to draw the progression of this atomic theory and see if you understand what happened in each of these phases of the theory.